Howdy Bike 410 students, this is video 5 of chapter 12, and by now you've watched both of the Khan Academy videos, and so you're familiar with the Michaelis-Menten equation, which is where we last ended on the last slide on video 4. So just to reiterate, the velocity or the initial velocity is equal to the maximal velocity, Vmax, times the substrate concentration over Km plus the substrate concentration. So that you're going to want to remember in order to use it to solve equations. All right, so what is actually going on when we're looking at the rates of reactions as a function of substrate concentration? Well, what actually happens in the lab is you measure initial velocities as product formation as a function of time. Okay, so this is the actual raw data that we're looking at here. We're looking at the rate of product formation on the y-axis, and we're looking at time on the x-axis. And what we want to take from this data is the slope of the tangent to that rate. And so let's go through it one substrate concentration at a time. So you're the graduate student and you're sitting in the lab and you are measuring the product formation as a function of time using a spectrophotometer if it's a color reaction. And so at the first substrate concentration, 1 is 0.2 micromolar or 200 nanomolar. And what you observe is that there is an increase in product formation that sort of flattens out as a function of time. Okay, so then once that experiment is done, you do a second experiment. And in the second experiment, your substrate concentration is equal to 0.5 micromolar. Ignore this for now. Okay, so at 0.5 micromolar concentration of substrate, you do the same thing. You plot the formation of that colored product as a function of time. And then at the third, and usually you do many more substrate concentrations, usually in the 20 or 30 different experiment range. But for this simple example, we're looking at the third substrate concentration at 1 micromolar, and you can see that it has a faster rate of product formation. So if you pick any time, let's say right here, let's say this is 10 seconds, you can see that there's a lot more product being formed at 1 micromolar than at 0.5 micromolar or at 0.2 micromolar, right? Okay, so you have higher initial velocity at increasing substrate concentration. Now, the reason that this turns over and becomes flat is because you're running out of substrate. So your substrate concentration is obviously not constant through the reaction. So the valuable information is the initial velocity, and the initial velocity can be determined from the slope of the tangent to the line. Okay, so once you're finished with all of your experiments, you plug in your algorithm to give you that dotted line that you're looking at here. Let's look at the highest rate at 1 micromolar. You're looking at this dotted line here, and the slope of that dotted line is equal to your initial velocity for your substrate concentration. I don't want to put that for substrate concentration number 3. Okay, so this is for test number 3, so M3. M2 would be the second dotted line, and that first dotted line would be to M1, right? So each of these dotted lines has a slope. Slope, if you remember, is M, and the M value is the initial velocity. So that's the actual experiment. Those are the raw data. And you're going to plot your Michaelis-Menten plot uses those M values, those slopes, as a function of your substrate concentration, okay? M equals a function as a function of substrate concentration. And that function is the Michaelis-Menten equation. Okay, so let's go back and look again at what's going on in the reaction. We have the enzyme. We start with the constant concentration of enzymes. So all of these experiments and more were done at 1 constant enzyme concentration. Okay, constant. But you're doing each experiment at a different substrate concentration, etc. All right. So at a constant enzyme concentration, you're looking at this reaction, the enzyme binding to the substrate and then either unbinding, if you go backwards, or going forwards, forming product. And it turns out that when you plot this using the Michaelis-Menten equation, you see two different things going on. At low substrate concentrations, you're going to see a rate, an initial velocity that is proportional to the substrate concentration, okay? Where have we seen that before? Where have we seen a rate that's proportional, a rate of product formation that's proportional to the substrate concentration? We saw that with radioactive decay, that first order reaction. So this is a pseudo first order part of the Michaelis-Menten plot. And so at low substrate concentrations, this is very important, you have a pseudo first order reaction where the initial velocity appears to be proportional, directly proportional to the substrate concentration. So that's the linear part of our Michaelis-Menten plot. But then as you go higher in concentration of your substrate, you begin to approach zero order kinetics, where there's no more change in the rate. Okay, so in that case, zero order kinetics means zero change in the rate, which means that your initial velocity is equal to your maximal velocity. This is also linear, but this is flat, or zero change. Okay? And the reason that there's no change at high substrate concentration is because at very high substrate concentration, the enzyme is saturated. So let's say you have 100 enzyme molecules, but you have 100,000 substrate molecules. So you're so saturated, every single enzyme that binds to substrate that goes on to form product is just rebound immediately by substrate again. So the enzyme that's there is already working at full tilt. Where have you seen saturation before? You saw it when we talked about transport. Anytime we transport a solute across a membrane using a transporter, those integral membrane proteins that either facilitate or actively transport solutes are going to be saturated at very high solute concentration. So that rate of transport across the membrane will no longer be sensitive to adding more and more solute because they're already working at full tilt. You've already gone way above the limit concentration of the transporters. Same thing's happening here. You go way above the concentration of the enzyme and you don't get any improvement on the product formation because every enzyme is already working at its maximal capacity. It's saturated and you reach Vmax, or you approach Vmax. Now remember the rate constants. Rate of formation of ES is described by the rate constant K1, and its dissociation back to E plus S is K minus 1, and the product formation is K2. You're going to need to remember which K's go with which step. All right, so this is the Michaelis-Menten equation. So this is a lot, so I want to break it down for you step by step. So remember when you were the graduate student measuring all of those rates, sitting at the spectrophotometer and looking at product formation as a function of time, and you took all of those slopes, and those slopes, the value of those slopes was equal to the initial velocity at each one of your enzyme concentrations. And so that's what each of these black dots represents, the slope, okay? Each one of these black dots represents the slope that you measured in those experiments. So this is not raw data. This is the analysis, okay? This is the analysis of the data that you took when you looked at product formation as a function of time. All right, so each one of these black dots is equal to the M value, or which is equal to the initial velocity at a specific substrate concentration. So now, instead of time on the x-axis, you have substrate concentration, and you're going in increasing substrate concentration on the x-axis, and and the y-axis is your initial velocities, your m values. Okay. All right, so there's some other stuff written on these slides, but I first want to look at the blue line. I want to draw your attention to low substrate concentration. And yes, substrate concentration is given on this slide as multiples of Km, but don't worry about that right now. Just keep in mind that the x-axis is this increasing substrate concentration. At low substrate concentrations, it appears that the initial velocity, that slope that you measured, is increasing, and we can add a couple dots. You know, if you're a really diligent graduate student, you would measure a whole bunch of initial velocities at this early time in order to see that you have a very accurate description of that pseudo first order part of the plot. Okay, so at concentrations below the Km, you're in that pseudo first order, which is just a fancy way of saying that it's linear. So the initial rate of your enzyme catalyzed reaction seems to be linear at concentrations of substrate below Km. Okay, so what's Km? You know from your Khan Academy video that Km is equal to the substrate concentration at 1/2 of the maximal velocity. Okay, Km is other things too, but we're focusing on this, and I'll have a slide about all the things that Km represents in the upcoming slides. Km, the Michaelis constant, capital K sub m, is the concentration of substrate. So it's in substrate concentration units in molar, at which your initial velocity is 1/2 Vmax. Okay, and so that's why this picture shows Km on the x-axis. It's at that 1/2 Vmax. So what you can do is you find your maximal velocity here. You calculate your maximal velocity. It's that number that your rates are approaching asymptotically, and you divide it by 2, and then you drop down to the substrate concentration, the x-axis, and that will be your Km value. Okay, so your Km value is a substrate concentration. It's not a velocity. All right, so let me erase all of this. So let's talk about Vmax. At Vmax, you're at saturating substrate concentration. So as you go way above Km, 2 Km, 3 Km, 4 Km, 5 times Km, you know, much, much higher than Km, you're no longer looking at a linear relationship between the velocity of the enzyme catalyzed reaction, or to put it more simply, the rate of product formation. It's no longer linear with increasing substrate concentration. It's starting to plateau. And the reason that it's starting to plateau is because you're saturating the enzyme. You're so much higher in substrate concentration that you have already occupied every enzyme active site immediately after it becomes available again. So the enzyme is already working at full tilt. And because enzyme catalyzed reactions aren't synchronized, we don't fill up all of the enzyme active sites and then start them at the same time. In reality, Vmax is never achieved. You just asymptotically approach Vmax at increasing substrate concentration. Okay, so what have we learned on this slide? We've learned that below Km at low substrate concentration, the relationship between product formation and substrate concentration looks linear, and so we call that pseudo first order, and it's very sensitive to substrate concentration in this range below Km. But then as you go above Km, it's no longer as sensitive to substrate concentration, and it begins to flatten out. That's the zero order or zeroth order, because you are saturating the enzyme with substrate. Okay, so pseudo first order below Km, so this is below Km, and zero order above Km. Okay, that's what this is showing us on the Michaelis-Menten plot. So you can see that enzyme catalyzed reactions are nonlinear, but they look linear at low substrate concentrations where enzyme is not limiting, and then they look flat at very high concentrations where the enzyme is saturated.